Okay, so we've already talked about how polar graphs and polar coordinates work. Now let's start extending some of the basic ideas of calculus to this context. Remember, things that are inherently round or driven by angles, it's often easier to understand them in terms of polar coordinates. So there's natural motivation in many areas to work with polar coordinates, but we still want to answer questions like, what is the slope of a tangent? That gives us a sense of the direction in which a graph is changing. How long is a portion of the graph in terms of its arc length? And what is the area of something defined by a polar curve? And here I'll just note that we'll be thinking about this notion of within a curve rather than under a curve. Okay, so this first one is slope. And there's actually no special formula. We know how to find slope for parametric equations, and we can just treat this as parametric where theta is the parameter. Usually we call the parameter t, but if you just look at this expression here, that's how we found slope for just a generic parametric, although I have a typo here, so let's fix that right away. This should be dx d theta. And we'll remind ourselves that y in polar is the same as r sine theta. So this is y, it's the same as r sine theta. This is x, it's the same as r cosine theta. And assuming we have a formula, we can fill in specifically what is the formula here just in terms of theta, what is the formula here just in terms of theta, and then do the derivatives. It might not work out to something clean, but the concept is straightforward. You just do it like it's parametric. So let me add a page here. So here's just an example to watch. So for the cardioid, r equals 2 minus 2 sine theta. Find the slope of the tangent at theta equals pi over 4. So I'll copy it here. And let's just look at this graph to get a sense of what's going on. Here I have 2 minus 2 sine theta. Let's see, I think I can just write theta equals, oops, there's a theta key there. Theta equals pi over 4. I'm not doing this with my keyboard, so it's a little trickier. Let's try. I think if I just type pi, it'll recognize that. Great. Divided by 4. Oh, it doesn't like that. Here's what I'll do. I'll just draw the line y equals x. Y equals x follows that 45-degree direction. So, oops, change this. So I've altered this a little bit, but there's a point there of intersection. And at that point of intersection, let's change the color here. Right, we have a vague sense at that specific point on the graph where these two meet. What is the steepness of that red line? Just eyeballing it, it's going to have a positive slope, but not a big one, right? Something in the neighborhood of 1/2. Maybe it'll work out to something really nice like that. We're going to have to do the work, right? But we want to understand the idea here. We're trying to figure out how steep is the red graph at that crossing point. Okay, so we know that dy over dx is just the derivative of y with respect to theta over the derivative of x with respect to theta. Y, of course, is the same as r sine theta. X is the same as r cosine theta. And we know, for this particular example, what r is. So here we would have 2 minus 2 sine theta times sine theta. And down here we would have r, which is 2 minus 2 sine theta, times cosine theta. And let's distribute before we take derivatives. I don't think I promised that this would be fast, but conceptually, there's nothing really you have to wrestle with. You just say, oh, I do this like it's a parameter, and I use what I already know about polar coordinates. Okay. So finally, we can take the derivative. Up top, the derivative of sine is cosine, so we have 2 cosine theta minus 2 times derivative of sine squared would be 2 times sine theta, and then by the chain rule, cosine theta. In the bottom, derivative of cosine is negative sine theta minus 2 times, and I'll do product rule here, derivative of the first times the second minus the first times the derivative of the second. Actually, give me a second. Plus, well, I don't know why I did that, sorry, plus the first times the derivative of the second. Okay, I'm not going to simplify this, I'm just going to plug in right away. So at theta equals pi over 4, let's evaluate and see if this works out to anything reasonably nice. Dy over dx would be 2 times the cosine of that angle, which is root 2 over 2. Right? Luckily, all our sines and cosines are the same number. And then we'd have minus 2 times 2 is 4 times sine times cosine. I'll just write it all out and simplify it later. We'll see what it works out to. Minus 2 times sine of pi over 4 minus 2 times cosine times cosine minus, if we move out this negative, sine times sine. That's actually convenient there. So if we keep simplifying, up top, we have root 2 minus, you'll notice this 4 cancels with the 2 times 2, so we're left with root 2 minus root 2, which is 2, over minus root 2 is what we get if we simplify this part, and then this is all 0. Now, if we break this into 2 fractions, I do want to point out this is going to be expressible in a nicer form. This first part is negative 1, and this second part is root 2. So this actually reduces to a reasonably easy number to write down, and that number is approximately 0.414, which is close to our observation, right? Positive slope, but not very big. I estimated it was roughly a half. So don't get too worried about all the steps. Sometimes it'll be a lot of steps, sometimes not so much, but really just think about what did we do. We reminded ourselves, when I have a parameter, this is how I take slopes. And in this case, we just treat theta as the parameter. Remember what y is, remember what x is, make our substitution, and then hope it's not horrible. Okay, so the version I've given you hopefully will be easier. For the spiral r equals theta, find the first positive value where the curve has a horizontal tangent. So let's look at that graph. I'll put this one away here, and we'll hide this. Here is our spiral. So we notice somewhere around the top, right at the very top, that's where we have this horizontal tangent. And we want to know where is that in terms of which value of theta. Let's just switch back here. So our spiral looks something like so. Right? And we want to know which value of theta is the location for where we have that horizontal tangent, which would also be the topmost point of the first loop around this spiral. So hit pause and see what you can come up with. Okay, let's take a look. So we know the slope of the tangent would be derivative with respect to theta of, I'll just skip the intermediate step, r sine theta, which is y, over derivative with respect to theta over our cosine theta, which is 0. Now we want this derivative to be equal to 0. And fractions would be equal to 0 when the top is equal to 0. So what we actually want here is just that this numerator is equal to 0. And r is the same as theta. So we have theta sine theta equals 0. So let's take that derivative by the product rule. Derivative of the first times the second plus the first times the derivative of the second is equal to 0. And you cannot solve this by analytic techniques, right? Once you have the angle and cosine of an angle sort of intermingling, unless it happens to be some really special thing where you notice 0 is a solution or something, you have to solve this numerically, right? We will estimate the solution. So obviously you can't see me do this, but I'm doing numerical solve on my calculator. I'm just going to call the variable x because that's faster to type. So we have x times sine x. I almost got that error where it was confused because I typed x. Oh, sorry, it's not x sine x. I want to know when is sine of theta. Again, you can't see this, sorry. Plus x times cosine theta. I do need that cosine or the calculator gets confused. I want to know when is that equal to 0. And I want to solve that for x. Okay, I got 0. So let's do a little bit better, and I need to add bounds on this. So well, it's definitely in the second quadrant. So let's look between, say, theta equals 1 and theta equals 4. That'll certainly cover the whole second quadrant. And we get that theta is approximately 2.029. This is not a familiar value. If we look at roughly what this graph looked like, our spiral is something like this. And yeah, remember, this is pi radians. Pi is a little bit bigger than 3. So it is very believable that this angle is roughly 2. Right? Because it's certainly in the neighborhood of 2/3 of pi. Okay, so we've talked about slope. What else are we going to talk about? Arc length. Again, we know how to find arc length when there's a parameter, and we can treat theta as a parameter. So you could do that. You could say, all right, I know when I want to find arc length, I'm going between here and here, where these are values of theta. Derivative of x squared plus derivative of y squared, all under the radical, and I do that. Now, I am going to show you something. Maybe just watch and appreciate this. Don't feel like you have to copy everything. I'm going to do some work on this. Making this, oops, I'm going to make this giant. And maybe just watch and think about what I'm doing. It turns out for this particular example, if we roll up our sleeves and simplify this, it works out really nicely. And it will be easier to memorize the nice version, right? So there is sort of a trade-off. If you don't want to memorize anything new, you can do this because it's just applying the way of doing arc length that we saw before to a new context. But it will be easier if you learn a separate formula. Let me show you where that formula comes from. So the first thing we're going to square here is what we get when we take this derivative and its product rule. So, remember, theta is the variable. So it's the derivative of the first times the second plus the first times the derivative of the second. Now, we'll ask ourselves, what's this derivative? So derivative of the first times the second plus the first times the derivative of the second. Now, let me FOIL this out. So if I FOIL this out, when I square the first one, I get dr d theta squared times cosine squared theta. My middle term would be, oh, there's a negative in there. So my middle term would be 2 times the product, but there's a minus. So minus 2 times dr d theta times cosine theta times r times sine theta. And then when I square out the second part, I would get r squared times sine squared theta. Let me see if I can just shrink down just this part. Again, maybe just realize that I'm doing math you know, and it's going to work out really nice, right? One person does all these hard work, and then you just have to remember how it simplifies. I'll FOIL out this part. Derivative squared times sine squared. My middle term would be 2 times dr d theta times sine theta times r times cosine. And then my last one would be r squared cosine squared theta. So let's just take a look at what we have here. These that I'm highlighting in yellow are opposites. So I'm left with 4 terms. 2 of them have the derivative squared, and 2 of them have r squared. I'm going to factor this out. So dr d theta squared, and that's multiplied by both cosine squared and sine squared. I also have r squared. That's multiplied by both sine squared and cosine squared. And hopefully you realize, oh, wow, cosine squared plus sine squared is 1. So what we have here is dr d theta squared plus r squared. So if you want something that's more straightforward, what you're actually doing here, right, this is probably the version you want to learn because it does require a little bit of memorization, but it is easier to use. We're just taking the integral between whatever angle bounds we have of the square root of dr d theta squared plus r squared d theta. It's a little bit messy. This is the version you probably want to know. Okay, so let's look at an example. Find the full length of the limacon. Right, that's a fancy word for this kind of shape. R equals 1 minus 2 cosine theta, including its inner loop. So this is what it looks like. It has that inner loop because sometimes r is negative and it makes something go backwards. So let's just draw roughly what it looks like. You'll notice along the x-axis, the intercepts are at -3 and 0. So it has this inner loop like so, and then it does this. And I will point out that what we have here is the full range from 0 to 2 pi. What's happening is for certain angles, right? So here's what's going on. In the first, actually, let me go back to what this graph looks like. It does have a little bit in the first quadrant and fourth quadrant, so I want to draw that more accurately. I don't want to throw you off here. Here's what's actually happening. if you plug in 0, so let's experiment a little bit. If theta equals 0, then r equals 1 minus 2 times cosine of 0, which is 1 minus 2, which is negative 1. Okay, so that's actually where we are right away. Then what happens as we move through the first quadrant, we start with some negative values of r. So we're going backwards. Backwards in the first quadrant actually draws it in the first quadrant. Then we get some small positive values. Then as we enter the second and third quadrants, we get big positive values. Then we get small positive values. And then at a certain point, this becomes negative again. But what I want to point out, which is nice, is in order to draw this entire thing, half of the inner loop, the whole outside, and the rest of the inner loop, we're going from 0 to 2 pi. Very often, if you're dealing with a cardioid or a limmason, you are just going from 0 to 2 pi to do a full length. So what we're going to do here is we're going to say that the arc length, the full perimeter around this, would be the integral from 0 to 2 pi of dr d theta squared plus r squared d theta. And let's see how much of this we can do by hand. So the derivative of this would be 2 sine theta. Derivative of 1 is 0, derivative of cosine is negative sine. So we have 2 sine theta squared. And then we will square out this part. If you know you're ultimately putting this in your calculator, you could do it now. I want to demonstrate that this at least a little bit simplifies. This is 4 sine squared theta. This, when we FOIL it out, is 1 minus 4 cosine plus 4 cosine squared theta. We have another example of sine squared and cosine squared, which we could combine, and we would actually just have 4. So this thing plus this thing is 4, because it's just 4 more than the usual sine squared plus cosine squared. And then we could add that to 1. So we're integrating here the square root of 5 minus 4 cosine theta. It is possible, if you are very clever, actually I take that back, it is likely, if you are very clever, there's a way to do this by hand. But I would struggle for a while. Right? So let's just do our calculator. We will go to my calculus menu, do an integral here from 0 to 2 pi. And I am integrating the square root of 5 minus 4 cosine theta. And what I got here is 13.365. And let's just test, does that feel plausible? This point right here is at -1, 0. So this is traveling 1 unit in a curved way. This is traveling 1 unit in a curved way. Just this inner loop is probably around 3. And then for the rest, right, the rest is kind of like a circle that has a diameter, right? Not really a diameter, I'm cheating and putting it in quotes. Diameter of roughly 3. So if that were a circle, its circumference would be 3 pi, which is 9-ish. So, you know, the outer part feels like it should be around 9 or 10. The inner part feels like it should be around 3. This is a very plausible number. We would never know for sure without doing the calculation, but this is not an answer you should be suspicious about. So many of these, ultimately we pull out our calculator. All right, now, what about area? So here's the thing about area. We really need to change our perspective. Because when you first started learning about how our integrals related to area, the canonical example involves finding the area under a curve. But suppose we're working in polar coordinates. When we're working in polar coordinates, we have these things that are essentially round. What if I actually just draw something similar to what we had before? I take that. Let's draw a cardioid. So I apologize if you're copying all of this, but something without an inner loop would be easier to understand. Right? What if we have something that looks kind of like this? What we could do in this case is we could think, all right, maybe here is theta equals A. It specifies a direction. And here maybe is theta equals B. And I would want to find this area. Right? It's not the area under the curve. It's the area inside the curve. And it starts at this ray or radius coming out of the origin, and it ends at this one. That's what's happening. It's not between two vertical lines. It's between two lines coming out of the origin and what's inside. Obviously, we can start modifying this to figure out what's the area between two polar curves once we get good at this, but this is the basic setup. So let me show you how we would do this. Right, so I guess I've kind of drawn the picture. Up to you how much of this you want to write down. What we're going to do, which is a very familiar idea. Let's imagine we have some polar curve like so. And here is theta equals A. And here is theta equals B. When we were first learning Riemann sums, we said, oh, you know what I'll do? I will approximate this area using the areas of rectangles, because I know how to do that. And then I will run a limit, and that turns that sum into an integral. So we imagine if I break it up into a lot of rectangles, that'll be pretty close. Here what we're going to do is we're going to break it up into a lot of sectors. A sector is a fancy word for a pie slice. If I have a perfect circle, a sector is this region between two radii. So this is not a circle, right? There's not a consistent radius. This distance here looks like it's longer than this distance here. Right? As I'm moving along, r is not the same. But we're going to break it into sectors as though they are the same. So the idea is maybe I have something like so. And let me change the color. Again, probably best just to watch this and understand theoretically what I'm doing. You don't really have to have all the details. So imagine that we're just looking at the pie slice between these two. I could cheat a little bit and say, what if I pretend it's perfectly circular? So let's imagine that what I have here is truly a sector, right? It's a pie slice. The radius is the same on both. Make this a little bit smaller so I can shade it. This is just a demonstration. At a certain point, if you're painstakingly copying this, you're probably making a bad choice. But I want you to at least see once where this comes from. And then at our next one over here, we could say, all right, maybe between this radius and this radius, I'll again pretend that I have a pie slice. Pretend that I have a sector. I'll draw maybe one more. And hopefully what you can start imagining is if I have a bunch of these, probably the combined area of all of these sectors is similar to the true area I'm trying to find. It's not perfect, but if I have a bunch of slender sectors, then presumably, so I'm going to just do these really fast now, right? Pretend it's a sector, pretend it's a sector, pretend it's a sector, pretend it's a sector. Right, and maybe we'll do one over here. If I took the combined area of all of these sectors, it would be similar to the area I'm trying to find. Obviously not perfect, but if I had a bunch of them, it would be pretty close. Now let's just imagine here that this is change in theta, this is change in theta, this is change in theta. Let's imagine it's always the same. All right, so now let's think about how do we actually find the area of a sector? Here, we would have R, and that would be a formula that we get from theta, right? So it would be what we get if we plug in a particular theta. So here we could imagine, okay, here is my first value of theta, I'll call that theta 0. Here is my second angle, I'll call that theta 1. Right? Every so often we are getting a new value for that angle. Just like we would do with x's. Oops. Right, for area under a curve, you probably remember, oh, here's x0, here's xn, here's x1, here's x2, here's x3. We're just breaking it up. And we're finding the heights at individual x's. Here we're finding the radii at individual x's. So this is just the radius as a function of theta. And we're saying that this is delta theta. Okay, how would I find this area? Well, area of a circle is pi r squared. But we don't have the whole circle. We have a fraction of the circle. It would be 2 pi if we went all the way around the whole circle. But we're not. We're only going this far. How far is that? Well, as a fraction, it's whatever this changes, delta theta, over 2 pi, times the area of the whole thing, right? Area of the whole circle times the fraction we're actually taking. So what we would have here is, and you'll notice the pi's cancel, 1/2 times r, which is actually what we get from plugging a value of theta into the formula, delta theta. And then we would be adding together a bunch of these. There are a bunch of sectors. The way I figure out the area of each sector is the same, right? So this is our approximation. But then the true area would be a limit. One way of doing it would be the limit if I just take more and more of these sectors of what we just did here. Oops. No, I'll just rewrite it. Oh, so that's actually k, not theta. K is going from 1 to n. We have 1/2 times whatever the radius is at the time squared. And we're adding all these together. But the form here is limit of a Riemann sum. By definition, a limit of a Riemann sum gives us a definite integral. So this turns into the definite integral from our first value of the angle to our last value of the angle of 1/2 r squared d theta. When we make this leap, it just becomes the function r instead of individual values, and the delta theta kind of turns into a d theta. This is a pretty easy formula. You're going to have to learn it. Maybe it's not super intuitive, but it's not hard to remember. If we want to find polar area, we essentially integrate 1/2 r squared. All right, and here we go right here. So it's already written down for you. I've said it out loud. This is the version you want to study. So let's look at an example. And again, I'll just show you one. Let's find the area inside the inner loop of that limacon we were looking at before. Something like so. And depending upon our point of view, this inner loop starts at a place where the radius is 0. Imagine it going around. And it ends at a place where the radius is equal to 0. So to find the starting and ending points, because I'm not telling you at which angles we should begin and end, but for things like loops, they begin and end when r equals 0. Right here, r equals 0, and then we go out and come back, and we're getting this little area here. It comes from negative values of r, but it clearly is an area. So this happens when r, which is 1 minus 2 cosine theta, is equal to 0, which means 1 equals 2 cosine theta, which means cosine theta is equal to 1/2. And one nice way of thinking about that is theta could be negative pi over 3 or pi over 3. So the idea is we can imagine here is the direction theta equals negative pi over 3. And here is the direction theta equals pi over 3. It seems like there's nothing in this zone because this is the zone where we go backwards. But the backwardsness begins here and ends here. So we would have, to find our area, the definite integral from negative pi over 3 to pi over 3 of, here's our formula, 1/2 of the r function squared. Now you may feel like we're still doing something wrong because it's backwards. The good news is that the squaring means that it's no big deal that r is negative. The squaring will turn it into a positive, whether we've drawn it forwards with a positive value of r or backwards with a negative value of r. In theory, if we foiled this out and you did some clever substitutions, it's doable by hand. As I'm making this video, I think you don't know all the tricks yet, so let's just feed this into our calculator. Something that I will point out, which is just occasionally helpful, if you notice symmetry in a problem like this, you could say, oh, this is 2 copies of the top part, right? There's a top-bottom symmetry. So this part here and this part here are the same area. I could really just go from 0 to pi over 3 and take 2 copies of that, and we would notice the 2 and the 1/2 cancel. If you notice that all at once and just do the cancellation in your head, it saves you a little bit of time. If you go to the point where you're doing a lot of multivariable calculus, it is often extremely helpful to notice symmetries and just take one smaller integral and then multiply it. If you have 2-part symmetry, just do the easy part, double it. If you have 4-part symmetry, do the easy part, quadruple it. But I'm just going to put this in my calculator. So we're going from 0 to pi over 3. And we are integrating 1 minus 2 cosine of theta sorry, I mistyped something, squared. And this works out to approximately 0.543. Is this plausible? Well, let's just remind ourselves that this is at negative 0, and the 1's comma 0. So if we pretended that this was a circle, it would kind of be like a circle where the diameter is equal to 1, and so therefore the radius is 1/2. So the area would be pi r squared, which is pi over 4, and pi over 4, yeah, it's approximately 3/4. We know it's actually shorter than a circle, so it should be a little bit less than 3/4. About 0.543. This seems believable. It's the right kind of number. There's really no way of saying like, oh no, it should definitely be 0.57. It's the right kind of number. All right, so here's one I want you to try. Find the area inside one petal of the graph r equals sine 3 theta. And I'll show you what that looks like so you understand. R equals sine 3 theta looks like this. It has symmetry. I've changed my grid just a little bit, so maybe it doesn't look like perfect 3-part symmetry, but it really does. Maybe I can fix that. Maybe too late. So what is the area just inside one of those petals? Think about how you might get that. Okay, so the trick, of course, is to figure out at which angles does an individual petal begin or end. An individual petal begins or ends when r equals 0. So we would need to think sine of 3 theta is equal to 0, which means 3 theta is 0 or pi or 2 pi, etc., which means theta is 0 or pi over 3 or 2 pi over 3, etc. So hopefully you can believe, okay, it looks believable that this first petal begins at theta equals 0, begins perfectly horizontally, and then it ends when we're pointed in the pi over 3 direction. I will point out what happens after pi over 3 is that the sign values become negative. Positive values of sine of 3 theta until we get here, then they become negative, so it goes over. I think I've drawn this poorly, actually. Don't worry about that. But we have figured out where this particular petal begins and ends. So our area is the integral from the angle at which we begin to the angle at which we end of 1/2 of r squared. And again, this is theoretically doable if you know enough tricks, but let's just put this in the calculator. And I'm getting that this comes out to approximately 0.262. My picture here isn't all that great. I will tell you that this distance right across is 1. So if you kind of imagine this as being part of a rectangle, if this distance is 1, this distance is less than 1/2. So this rectangle it presumably has an area less than 1/2, and we're even smaller than that. So again, this feels like the right kind of number. It's definitely smaller than 1/2 based upon our picture. It's hard to say how much less. Okay, this was a very long video, but we have gotten through all of it.